Well, hello and welcome. Uh, I have come here on a rather cold day, and the sun is out, so I am out as well. And I'm going to take up the first problem of NMTC, round two, which happened the last year. And the problem is one that of number theory. And the problem says uh, m and n are positive integers. Find all pair of positive integers m comma n such that m square plus 3n and n square plus 3m, which are both perfect squares. So that's a question. So before I go ahead, and let me tell you this, that there are many important ideas in number theory, but a few important ideas that I must talk about is that one is ordering, that you should order numbers. Order का मतलब होता है कि that something is greater than something, or something is greater than or equal to something. That's one thing. And the other thing that you should take care of is that GCD. Quite often, if there is a problem about number theory and you think about GCD of a few things, usually you make some advances in that problem. आप कुछ advance तो कर ही लेते हो उस problem में. Let's have a look at this problem. So it says that m and n are positive integers, and m square plus 3n and n square plus 3 are both perfect squares simultaneously. So first case which I'm going to deal with is that what if m is equal to n? Oh, well, if m is equal to n, then we're dealing with m square plus 3m is a perfect square. That's the question. That's the only question, that m square plus 3m is a perfect square. And well, uh, this is true for m equal to 1. So if m is 1, then m square plus 3m is 4 and it's a perfect square. A perfect square. So m equal to 1 is a solution. And since m was equal to n, so one of the ordered pairs that we have is 1 comma 1. Right. Now, what happens if m is not 1 and m is in fact greater than 1? So if m is greater than 1, then you can see that m square plus 3m is in fact greater than m square plus 2m plus 1. Yeah, because m square plus 3m can be thought of as m square plus 2m plus m. This number can be thought of as m square plus 2m plus m. And since m is greater than or equal to 1, so this inequality holds true. And essentially that m square plus 3m is less than, in fact, m square plus 4m plus 4. Because m is a positive integer. And if you're curious that why I chose this number, and if you're curious why I chose this number, well, because these are perfect squares. So m square plus 3m is greater than m plus 1 squared and is less than m plus 2 squared. So m square plus 3n can't be a perfect square. Why? Because it lies between two consecutive perfect squares. Since m square plus 3m lies between two consecutive squares, so m square plus 3m can't be a perfect square. Right. So we're done with the case when m was equal to n. What is the case that we're left with? When m is greater than n. If m is greater than n, what happens then? Let's see. If m is greater than n, then m square plus 3n is obviously greater than m square, right? And this is less than m square plus 3m. Simple, because of the fact that m square, because m is greater than n. Since m is greater than n, 3m is greater than 3n, and so on. And that tells you that m square is less than m square plus 3n is less than m square plus 3m. It's further less than m square plus, as you might have guessed, 4m plus 4, which is equal to m plus 2 squared. Right, so what we have done is that we have confined this number, m square plus 3m, n, between two perfect squares, two consecutive perfect squares. So this number lies between m square and m plus 2 squared. And we were told that this number was a perfect square. Since this number was a perfect square and it lies between m square and m plus 2 squared, so therefore m square plus 3n must be m plus 1 squared. Right. So that tells you that 3n must be equal to rather 2m plus 1. Okay. And we have not used the fact that n square plus 3m is also perfect square. So now let's use the fact that n square plus 3m is a perfect square, and that perfect square is like maybe k square. K is a perfect square, something like that. Now, what do you want to do? How do you use the fact that 3n is equal to 2m plus 1? Right, so one of the ways is that you can multiply this by 3 and you can multiply this by 2. Uh, yeah, we can do that actually. We can multiply this by 3 and multiply this by 2 so that you can get the value of 6m, and 6n can be further replaced. Uh, if you were to do that, you'll get 9n is equal to 6m plus, since we have multiplied this by 3, so this is 3. And from here you get 2n square plus 3m plus 6m is equal to 2k squared. So you get 2n square plus 9n minus 3 is equal to 2k squared. And this is not nice. Why? Because we wanted perfect squares. And if you see the coefficient अगर आप देखेंगे तो this is not nice. These numbers should have been perfect square themselves. है ना? So I'm rather going to multiply this entire thing by 8. मैं इस पूरी चीज को 8 से multiply करने वाला हूँ. If you multiply this entire thing by 8, you get 16n square plus 72n minus 24 is equal to 16k squared. This is rather nice. Why? Because this is a perfect square, this is a perfect square. And in fact, this can be written as a perfect square. So this is 4n plus 9 squared, obviously, is equal to 16k square plus 105. That's what this translates into. Right, so 4n plus 9 squared minus 16k squared, and that's 105. And that's a rather easy equation to solve because that's perfectly factorizable. So this is 4n plus 4k plus 9 times 4n minus 4k plus 9 is equal to 105. And we can just assume that k is positive because that will not affect the value of n. If you replace k by minus k, you'll get the same thing. So that's not going to affect the value of n. And so if you see, then this factor, since n is positive integer, this factor here, it's greater than or equal to 17. So we want to write 105 as the product of two numbers, in which one of the numbers is greater than or equal to 17. Well, one of the ways to write that is that you can write that as, maybe 105 into 1. By the way, like 105 is 3 into 5 into 7. So yeah, one of the ways is that uh, 105 is 105 into 1. The other way is 35 into 3, right? Now what else we can do? Well, we can maybe 21 into 1, 21 into 5. We can't do 15 into 7 because this number has to be at least 17, right? So mind you that this is not the case that we are looking for because this number is of the form of 1 mod 9 or 1 mod 4. This is 1 mod 4. This is not 1 mod 4. So this is something that we're not interested in. So let's solve it. So either you have 4n plus 4k plus 9 is equal to 105 and 4n minus 4k plus 9 is equal to 1. And if you were to solve this, you'll get 8n plus 18 is equal to 106. And we get 8n is equal to 18 taken away from this is what? I guess 88. Yeah. Yeah. And 88, and so n is equal to what? 11. And if you were to put n as 11 here, so this is what? 33. And 33 minus 1 is 32. So m is equal to what? 16. Well, the other that you might get is 4n plus 4k plus 9 is 31. And 4n minus 4k plus 9 is 5. If you were to add them, you'll get 8n plus 18 is equal to 26. And you get n as 1 again. Uh, n equal to 1. If you were to put n is equal to 1, you'll get m equal to 1. But we have already considered that case. So there is nothing new. And we are done. So similarly, you can solve the other case in which n is greater than m. And you'll get the same answer. Just the values of n and m will reverse. So the ordered pairs which are possible are this and that. And we are done.